This is my fifth lecture. I am going to talk to you about P.V.T relations, pressure, volume, temperature relations. In thermodynamics, there are two types of parameters which can be directly measured. For example, pressure, volume, and temperature can be measured. Pressure you can measure the pressure gauge, temperature using a thermometer. But there are other parameters like enthalpy, entropy, internal energy, free energy, etc. They cannot be directly measured. But if you want to find out H, enthalpy, we can relate it to pressure, volume and temperature. Suppose you got an equation H as a function of pressure, volume and temperature, then you can easily calculate enthalpy. Therefore, what I am going to do, we have got two things now. One is to relate the enthalpy, entropy, etc. to pressure, volume and temperature. So once you relate this to this, then it becomes easy for us to calculate enthalpy. Because we don't have enthalpy meter, we don't have entropy meter, but you've got a thermometer, you've got a pressure gauge. So what in this chapter I am going to do is study P.V.T relations. What is the relation between pressure, volume and temperature? So in the next chapter, what I am going to do is relate all these unmeasurable parameters, directly not measurable, enthalpy, entropy, etc. to pressure, volume and temperature. So once you relate them to pressure, volume and temperature, you can easily calculate enthalpy, etc. Now, we've got what's called equation of state. Equation of state. It's of the form f of P.V.T equal to 0. P is pressure, V is volume, T is temperature. Therefore, any equation of the form f of P.V.T equal to 0 is called the equation of state. Now, the simplest equation of state is ideal gas law. Ideal gas law. Ideal gas law. Which says that PV equal to RT or PV minus RT equal to 0. This is a function of P, V and T. PV minus RT equal to 0 is the function of pressure, volume and temperature. This is the simplest form of equation of state. Ideal gas law is the simplest form of equation of state. Here pressure is in Newton per meter square. Newton per meter square. Volume is meter cube depend per kilogram mole. R is 8314 Newton meter kilogram mole degree Kelvin and temperature is in degree Kelvin. These are units in SI system. Pressure Newton meter square. Okay, so if you multiply this Newton meter square, will get cancelled to Newton meter per kilogram mole. Here Newton meter per kilogram mole. Multiply by temperature degree Kelvin, you will get Newton meter per kilogram mole. So it is 8314 Newton meter per kilogram mole. That's the units of R. Now, what does the ideal gas law says? According to ideal gas law, there are two assumptions in ideal gas law. One is intermolecular force of attraction or repulsion is 0. That means you have got a container, you got two molecules like this. When they are close to each other like this or far away, it doesn't matter because there is no intermolecular force of attraction or repulsion. They attract each other nor repel each other. So there is no intermolecular force of attraction or repulsion. Second assumption is that volume occupied by the molecule is negligible as compared to the volume of the container. For example, suppose the volume of this container is a 1 meter cube. Suppose I got two molecules and the volume is say 1 centimeter, cm key, 1 centimeter cube. 1 centimeter cube is very, very small compared to the total container. In such a case, we can say that the volume occupied by the molecule is negligible as compared to the volume of the container. Therefore, in ideal gas law, the number of molecules in the container will be low, very low. That's why you are neglecting the volume occupied by the molecule. Actually, suppose the volume occupied by the molecule is say a 0.2 meter cube. Then what is the remaining volume? 1 minus 0.2, that is 0.8. This is the volume available for the movement of the molecules. Okay. So here we assume that the volume occupied by the molecule is negligible. This is simplest ideal gas law. Second law is your Van der Waals equation. Van der Waals equation. Now this is of the form P plus A by V squared into V minus B equal to RT. Here A and B are called Van der Waals constants. A and B are called Van der Waals constants. Van der Waals constant. Now here A and B are called Van der Waals constant. This van der Waals equation takes into account the attractive forces between molecules. It does not consider the repulsive forces. Okay, it considers only the attractive forces between the molecules. So, van der Waals equation is a correction of the ideal gas law. If A and B are 0, what do you get? A 0, B 0, you get PV equal to RT. It gas law. So, if van der Waals constants A and B are 0, that means you get ideal gas law. Now, third equation of state. There are a lot of equations of state. See, where I'll tell you, give you one equation of state. Redlish-Kwong Kwong equation of state. It's of the form P equal to RT by B minus B minus A by T power half into V plus B. This is called the Redlish-Kwong equation. Here, A and B are called the Redlish-Kwong parameters. It's a modified form of van der Waals equation. Like this, we got number of equations of state. Now, fourth we'll take is D. We take what's called as virial equation of state. Virial equation of state. Now, it's of the form PV by RT equal to 1 plus B by V plus C by V squared, etc. So, B and C are called the virial constants. Is the virial constant. This is a volume explicit equation where volume is here. B and C are virial constants. If B and C are 0, we get ideal gas law. This is also of the form 1 plus B prime P plus C prime P squared, etc. This is also the equation of virial equation where B prime and C prime are called virial constants. But this is pressure explicit form. This is in terms of pressure. Therefore, it's called virial equation of state in pressure explicit form. This so here again B prime and C prime are 0, you get ideal gas law. Then the fifth equation of state, the number of equations I'm going to take only a few, is called based on compressibility factor. Compressibility factor. It's of the form PV equal to ZRT. Z is called compressibility factor. Z is called the compressibility factor. If it is equal to 1, then it is an ideal gas law. Z is equal to 1, ideal gas law. Z is greater than 1, it takes the repulsive forces between the molecules. If Z is less than 1, it takes the attractive forces. So this is your equation based on compressibility factor. Now, to calculate compressibility factor, there are a number of methods. One is called Z chart. Z chart or Z chart they call it. Now, it's a chart of Z versus PR. I'll tell you what is PR. The TR as parameter, reduced temperature. PR is called reduced pressure. It is given as P by PC, where P is the pressure and PC is the critical pressure. And TR is called reduced temperature, it is T by TC, where TC is called the critical temperature. So reduced temperature is T by TC, reduced pressure is P by PC, similarly reduced volume is B by BC. Critical parameters TC, VC and PC are available in any standard book on chemical engineering. Chemical engineering handbook is having, or anywhere you get the values of critical parameter. So once you know temperature, if you know the temperature, you know the critical property, then if you know pressure and the critical pressure, suppose this value is somewhere here. See, this is your temperature, this is your pressure, then you can read it and get the value of Z from this chart. This chart is available for your consultation. Now, this is the basics of your P.V.T relations. Now, I'll give one or two problems for you. Now we have got show that the second and third virial coefficient of van der Waals equation is given by B equal to B minus A by RT and C equal to B square. You try it out and let's see how you get it. Okay, you can try it out this. The number of problems are I won't do the problems. I will stop with this for the P.V.T relations. The next class I'll go ahead with the relating the thermodynamic properties to pressure, volume, and temperature. We'll stop with this.